All right, thank you everyone for coming. So yeah, today I'm going to be talking about quasi-isodynamicity, quasi-isodynamic stellarators. So the idea of the talk is not to give you a bunch of different ways in which you can define quasi-isodynamicity, but rather try to understand what the implications are of a stellarator when you make it quasi-isodynamic. So we are going to try to delve a bit deeper on what those consequences are and why QI stellarators behave the way they promise to. And we're going to try to do that in as broad a sense as possible to try to really delve into the physics of it. And then closer to the end, of course, I will mention near axis because I have to. And once I will present some examples illustrating some of the things that I had been talking about in the talk. With these fields being part of a new database that we created. So we'll get to that more practical aspect towards the end. All right, so let's start walking towards the concept of QI. Initial point, our stellarator. So stellarator, three-dimensional arrangement of a magnetic field. A plasma is inside. If this field is strong enough, we hope that the plasma is going to be confined for long enough. Now, I'm going to be specializing. So forgive me, Bob. I'm going to be specializing in something that just has nested flux surfaces, so labeled by psi. So level sets of psi define these nice onion layers. The magnetic field, the field lines, are tangent to these surfaces at every point. Now, the nice thing about it is that part of the discussion about the behavior of the stellarator can be done layer by layer, right? And this is good, so I don't need to be talking all the time about the whole 3D. I can just take one layer and say things about it. OK, so and because we are concerned with confinement, of course, we need to understand how the particles behave in the system. And this is the way how I'm going to walk towards the concept of QI in this first introduction to the talk. OK, so as I promised, we take our stellarator, we just focus on one flux surface. Our field length wraps around the flux surface. So to lead in all, we know that if the field strength is strong enough, our particle is just going to whiz around, move along the flux surface, right? So to lead in order, the description of the system, I can do onion layer by onion layer, right? And because I don't want to be drawing that 3D thing all the time, I can just, parameterize our surface in our usual theta phi. In this case, Boozer angles. So every time you see theta and phi in this talk, they refer to Boozer angles. And I can represent them on the plane. Now, the important thing about the Boozer angles that we need to keep in our minds for the talk is that our field lines, so this black line here, corresponds to straight lines, right? And in particular, we're going to assume that the slope of that line is some kind of rational number, so that the line covers the plane uniformly. So if I keep going, eventually, it's covering the surface uniformly. And this will become important, OK? Now, of course, it's not that simple, right? The plane itself doesn't look that clear. And in fact, the field changes over the plane, right? And so as the particles move around, they experience changes in the magnetic field. And in particular, because of the gradients of mod B, they feel this mirror force, right? So a particle is walking around the field and it feels a force that brings him back. A subset of particles are not fast enough along the field line, so they end up bouncing back and forth, right? And those are our trap particles, which are going to be the guys that we're going to be talking about for most of the talk. Now, to picture trap particles, because they are mainly moving along back and forth the field line, it's nicer to think of the problem a lot of the times not in the 2D, not in the 3D, but actually in the 2D, right? So I will represent a lot of the times the field in this way, so a magnetic field parameterized along L. Our bounce points, our trap particle will be bouncing back and forth between same values of mod B, which are labeled by this lambda, which is the trap particle class. Now, the fact that we are going to talk a lot of the times in 1D doesn't mean, of course, that the 2D is useless. Of course, the structure of these trapping wells on the 1D, it's highly determined by what things look like in the 2D, right? And in fact, we can classify the different fields, the different stellarator fields, according to what mod B looks like on the surface. And in particular, what the topology of the contours looks like. So first, we can distinguish contours that are clean and contours that are kind of ugly. So these are the ugly contours with defects. well, or piecewise homogeneous as well, which might not be ugly. But we are going to focus on what are called pseudosymmetric fields, because things have to be simple, so otherwise I wouldn't be able to do anything about them. So these are the simple contours, right? They can be poloidally closed, they can be toroidally closed, they can be helically closed. And because we are going to be talking about QI, we are going to specialize on things that have poloidally closed contours. We will see that this very choice has very important implications on the behavior of the field and on the physics of our stellarator. Okay, so far we've just talked about a single surface, we've just talked about a field line on the surface, but we know that the problem is not so simple. Particles, as they experience this in homogeneous field, they are also drifting, right? Our favorite magnetic drift. There's gradients in the magnitude of the magnetic field, and there's also our field lines are bent, right? So there's also curvature. And we know that as soon as we have these, particles no longer just stay on field lines, but they also drift from field line to field line, right? So generally speaking, if I wanted to describe what the behavior of the particles is or would be in a stellarator, I need to tell you about these two ingredients, right? What mod B looks like, what the curvature of the field lines look like. So some kind of sense of three-dimensionality of the stellarator. Now, as a matter of fact, I actually don't need that three-dimensionality to a large extent, and this brings me to the key ingredient in this talk. So this is the key ingredient that you need to remember for this talk. So there's nothing new here. This equation is just a different way of writing J cross B equals graph P. This is just the traditional force balance, but it's written in a way that will actually help us understand how geometry and mod B contours are actually linked together. And this will be important because a lot of the behavior, right, of the particles just depends on what mod B looks like to a large extent. Importantly, the key thing here is that the curvature of the field line, so if I take a field line, right, straight, I take the two ends and I bend it downwards, then there is a curvature of the field line, and therefore there's an associated gradient on the strength of the magnetic field. So if I take this, the magnetic field is stronger inside than it is outside, yeah? And in particular, this allows me not to talk about curvature, but just to talk about gradients of B. And so when I translate these to our drift, right, I can literally just think of the drift just in terms of mod B, right? In particular, how my particle is processing on the surface, so how I'm moving from field line to field line on the surface is mainly controlled by the radial gradient of mod B. And how I'm moving radially is just controlled by how things change on the surface, right? And this is key because if I would just want to talk about the radial drift, which is the main concern for as far as confinement is concerned, right? You know, radial drift is basically, if the thing is drifting radially very strongly, well, it's leaving the surface, so it's no longer really confining it. Well, I can just make that discussion just surface by surface, because as I was saying, all I need is the gradient of mod B on the surface, right? And so this is the key thing, right? So a lot of the discussion I can do layer by layer. Okay, so my particles are drifting radially. I would like them not to leave the system. And so this naturally brings the idea or the notion of this bounced average net drift, right? I don't care that much whether at every point the particle really leaves on the surface, but I don't want over time this particle to escape. So if I take my trap particles, they're bouncing back and forth, I average the net radial drift, I would like that to be kind of zero, right? And I want to emphasize once again that this behavior is uniquely determined by what happens on the surface. I don't need anything else, I just need the surface. And that's how we get to homogeneity and not homogeneity. So here's a bit of a definition. As I said, I can make the definition just on the surface. So I can call a function B as a function of theta and phi in Booster coordinates alongside these three scalar parameters, which basically describe what is the direction of this straight line, which is my field, my vector field. So the field is, this function is called homogeneous if for every pair of bounce points, and I do this averaging of the radial drift, is zero, right? So this is formalizing the notion of a confining field, yeah? And I can make this statement layer by layer. So when I will talk about as homogeneous stellarator, what I really mean is one in which each one of the layers of the stellarator satisfy this property. And as I did before, I took the space of stellarators and I divided them according to the topology of the mod B contours. I can do the same according to these properties. So I will have stellarators that are homogeneous and stellarators that are not homogeneous. And our favorite friend, quasisymmetric stellarators, I had to mention them. They live inside this bigger group of homogeneous stellarators. They satisfy or achieve this vanishing of the radial drift by having a direction of symmetry. So the contours of mod B would look straight, but we're not going to talk about them today. All right, so now I have two ingredients. I have my homogeneity, and I have my poroidal topology. I put this together, and that's my Qi. Okay? So the Qi is nothing more than a function on a surface, my magnetic field on the surface, that is both homogeneous, and the contours of mod B form poloidally closed contours. Okay, that is what I refer to as Qi, quasi-isodynamic stellarator. All right, so how do I then go on and study quasi-isodynamic stellarators? Well, the kind of the typical way of going about the problem is through optimization, right? So I want to find fields, equilibrium fields, that satisfy this property to a certain degree of accuracy. So I start from some point. I take my machine, I start cranking the handle, deforming the configuration, and trying to make it satisfy this very definition as close as it can, right? And out of that turning the handle, I get a whole set of approximately Qi fields, right? And so when I try to understand what are the common properties to Qi fields, I could just try to see through this set, right, and try to learn what they have in common, right? What properties they have in common, what things they have. But of course, this has a bunch of shortcomings, right? Homogeneity is quite a nonlinear, optimization is quite a nonlinear process. It depends very sensitively where you started. It depends how I carried out the optimization. It depends on what really I was optimizing for. And so one is always left with the question of what parts of what I get are actually intrinsic to the concept, or what aspects of that is just circumstantial, right? In the sense that it just depends on how I proceeded. So we would like to take a bit of a step back for now, right? And try to really understand which ones of those properties are actually intrinsic, inherent to being Qi, right? So that's what I mean by trying to understand Qi. So hopefully we'll get some of the physical sense of why it behaves the way it does, and then we can, frame observations in a practical scenario, having that framework set. All right. So let's go. Let's move on. All that was introduction. Let's start talking about really what Qi is. So that's our 1D field. Once again, the top one is just mod B. The bottom one is the local value of the radial drift as you move along the field line, right? So if we are to discuss homogeneity, right, which is one of the key ingredients of quasi-isodynamicity, it's key to start talking about bouncing, right, bounce pairs. Because as I said, homogeneity requires that when I take the radial drift and I average between bouncing points, it vanishes. So the first thing I need to do is identify bounce points. And naturally, this field line basically gets split into a bunch of trapping wells. Each one of them will have its left bounce points and right bounce points, right? And what determines this separation are turning points, right? So points at which the mod B has vanishing toroidal derivative. So dv, d phi is 0. And the question then is, what can we say about these points? Is there anything special about these points? What do they say about the system, right? And in fact, they are special. They are special because some trapped particles spend all of their life at these points. So this is the case of deeply trapped particles, which live at the minima. Of course, they are living at the minima, so they cannot move anywhere. So they just spend all the time there. And there's also barely trapped particles. These are particles that are approaching the maxima ever so slowly, so effectively they spend all of their life there. So if we want the field to be homogeneous, we don't want any of the particles to escape the plasma. Well, it better have a 0 drift at these points, right? Because otherwise, those particles will be flying away. So this means, remember that the radial drift is basically the poloidal variation of mod B on the plane. This means that at these points, both the toroidal and poloidal variation have to vanish. And this is very constraining. If we take this and translate it to the 3D, this is what happens. So I told you to bear in mind this all important equation in this talk. So I have my straight field line. If I bend it, it has a gradient of mod B, right? If I need places in which mod B on the surface does not change at all, well, I have a problem, right? Because if my torus is bent, it will have a stronger field on one side than the other. Of course, that means that there's a poloidal variation of mod B. And there's two things that I can do. One, I could take my flux surface and stretch it a lot so that the distance along the gradient direction is very, very narrow, so that that variation of mod B is small. And this, in fact, is what makes QIs try to make their surfaces ever so elongated. So there is a tendency for QIs to make their surfaces very elongated if you don't try to avoid it. That's the reason. Now, the second option is, of course, to have a straight sections, right? If I have a straight section, there's no curvature, there's no gradient perpendicular to the axis, and then I can happily live, right? So that's what confers the QI a bit of a spirit of a bunch of linked mirrors, and if you look from the top down, it looks like a weird polygon of sorts, yeah? Like that. Okay, so this was just talking about the points. So I've tried to avoid so far talking about homogeneity, and in particular, this fact that I have to average the radial drift between bounce points. This is the hurdle, right? This is the main hurdle when it comes to treating the problem analytically, because I have to be performing these bounce averages of this quantity, right? So how can I enforce homogeneity if I have to take all of these bounce averages? Of course, I introduce some kind of symmetry in the system, some kind of hidden symmetry. In this case, the symmetry, so think of each one of these trapping wells. The idea here is to make the radial drift an odd function with respect to the well shape, right? Because if I do so, then the amount that the particle drifts on the right is exactly the amount that the particle drifts on the left. I don't know why I did right and left, but and then that means that if this cancellation occurs for all the time, right, then there's no net drift. Now I've put this formally here in this quantity y, which is basically the radial drift times the amount of time that the particle spends in a differential amount of the field line. And the reason why I did this is because that quantity y that has to be odd, right, can be written this way. So it's kind of the poloidal derivative of B over the toroidal derivative of B. Now, if we translate this to the 2D, so let's go back and go from the 1D to the 2D, this means that I can think of QI in the following sense. So a QI forces the contours of mod B to have exactly the same angle, exactly the same inclination, exactly the same slope for every pair of bounce points. Yeah, so this is what I indicate by those color broken lines in there. So if I give you what it looks like on the left, you know how to complete the problem on the right. Now, this is somehow constraining because it's imposing a high degree of symmetry, but of course, I still have a lot of freedom, right? As I said, I can basically almost do anything that I want on the left, and then the other part of the plot is completed. And in particular, it still leaves quite a lot of freedom in terms of the relation between the toroidal behavior and the poloidal behavior. And this kind of high degree of independence between poloidal and toroidal behavior is key to QI. Now, it's true that there's a lot of freedom, but there's one point where we screw up, and this is at the maximum. So as I said, this symmetry means that if I take two bounce points, they have to have the same slope, right, of the contour. Now, if I take the maximum, this maximum is basically connected every point along it to every other point along it. So the only way that I can solve the problem is by making it straight. Now, this very concept, or this very argument, can be extended to its neighborhood. And if I continue this, then I'm only left with the straight contours. This is Kari-Sasharina 101. This is what they did. So I need to break homogeneity, right? I need to stop this propagation of my contour being straight everywhere, because else I would be talking about quasi-symmetry and not QI, right? OK, so I acknowledge that we need to break homogeneity. So when we talk about quasi-isodynamicity, we are actually not talking about exact quasi-isodynamicity. And as soon as I'm breaking this, I need some kind of measure to assess how bad this is, right? I need to have a measure that tells me or allows me to say, well, whether one configuration is very homogeneous and another is not. How am I going to gauge this, right? I need some kind of quantitative measure